at the parent rational function y equals 1 over x and the different transformations we can perform, and consider, does the order of the transformations matter in how the graph is going to appear? So I have a few transformations outlined that we can take a look at, and then look at some of the differences between them and see, is there a rhythm or a sequence that we can follow that we know is going to give us a good impression of the graph and how to use it and how to transform it. So let's start out with our basic. This is y equals 1 over x. We have all of our points in the first quadrant, as positive inputs will give positive outputs, and we have all of our points in the third quadrant where all of our negative inputs would give negative outputs. In our second graph, which I haven't activated just yet, we have a -2 in the denominator plus a 3 at the end of the function. We anticipate that this will move the graph of the function 2 units right and 3 units up, based on the transformations that you've reviewed elsewhere in the lesson. It will also move the horizontal asymptote and the vertical asymptote of the graph accordingly. So the x and y axis are now fair game in terms of possible intersections for this graph. So we move 2 units to the right and 3 units up. Here's the point 2, 3, somewhere in this space here. And we see that we would not cross the line x is equal to 2, and we will not cross the line y is equal to 3. We've moved the asymptotes along with the graph. Now, considering this as our graph, let's contrast that to the inclusion of the -1 in the numerator of the first part of the function. So now that 1 is a -1, everything else is going to remain the same. We activate that graph, and we see that it is a reflection over its horizontal axis. Because the horizontal axis moved up to y equals 3, we have flipped over that axis, and this red section of the graph is now up here, and this red section of the graph that was up here has now reflected down. I know it looks like it could also be a vertical reflection. That's because of the symmetry of the parent function. It is not a vertical reflection over the vertical axis. It is a reflection over the horizontal axis. All of those values that were below that horizontal axis are now above, and all those values that were above are now below. Now I'm going to put a temporary pause on that graph, and let's consider this fourth one down here. What happens if we put a negative around the entire function? Because truthfully, that's really how we learn how to make a reflection. The reflection that we typically study is the reflection over an axis, over the entire axis. And that's by taking the entire function and making it negative. And if I do that here, that's exactly what happens. The entire red function has now mirrored, not over its new horizontal axis, not over the line y equals 3, but it is instead mirrored over the x-axis itself. That's why this intersection point right here is the same in both of the graphs. That point had nowhere to go. Everyone else has reflected over the x-axis. These distances between the red graph and the purple graph are the same all the way down from the x-axis. That's because of the reflection. And then the same thing happens in these two parts over on the right, where we have this section that was up here reflected to be all the way down here. I hesitate to activate all of the graphs or more than one or two of the graphs at a time because I think it becomes a little bit cumbersome and a little bit difficult to see. But it would be worth accessing this file yourself, and it's available on our page. It's worth accessing this file yourself and manipulating the graphs and seeing the distinction between, sure, this is an easy transformation, up 3 and right 2. The difference between placing the negative just on the rational function itself, which flips it over the axis that it currently rides along, and putting the negative in front of the entire function, like we would in the last example. Obviously, the sign changes that would occur by the inclusion of the negative around the whole function makes a couple of other changes. So how can we do this, and how can we remember this, and how can we sequence this to have it make sense for us? Well, the easiest way that it can be explained is to attack the operations, or excuse me, attack the transformations as you would in the order of operations. So what's the first one that you reach? Well, the first one you would reach in the order of operations, if you knew what x was, would be the -2. Therefore, we expect the graph to shift 2 units to the right. And we can add that one in so you can see that's the 2 unit to the right shift. That's 2 units to the right. Then I can bring in the negative if I want to see the reflection, and I'm going to bring the negative just in this fraction, because then I get it to flip over. And after that, I will add in my 3 to make it move. The order of operations, if you knew what x was, would be to say -2, then worry about that first fraction, then add the 3. If you follow that transformation sequence, you should be able to place a graph, or at least have a visual of where it should be, depending upon any set of circumstances. Take your time, read through the transformations one at a time, and you'll be able to visualize where the graph is.